All right, let's see. What if our curves are best described in terms of functions of y? Let's say I've got this curve and this curve. Are those functions of x? No. Those are functions of y, though. So let's call this one f of y, this one g of y, because they're now no longer really best to describe as functions of x, but more as functions of y. And again, pointing out, if they're functions of y, they're x equals equations. X equals g of y and x equals f of y. So what if I wanted to know the area between those type of curves? Let's say I'm going, I think they say C to D here. Yeah, I've switched everything over to y's now, haven't I? No longer am I going to be talking in terms of x's, but in terms of y's. Well, the area between those curves then, f of y and g of y, how do you think we're going to do those? Well, it's not top minus bottom anymore. Which way do you think it should go? Right minus left, yeah. F of y minus g of y. Yeah, you want to do the right function minus the left function in those cases there. Because again, the integral of f of y gives you the area between the curve and the y-axis, so that would give you that area, and then g of y would give you that area. So yeah, you want to subtract f of y minus g of y, and we do want to go in terms of the y equals c and y equals d. Okay? All right, so let's do one of those. Find the area enclosed by x equals y plus 1 and y squared equals 2x plus 6. And I'm probably phrasing this question this way because that's one of the problems in the book, the way they phrase it too, because there's a couple of things on this. Do you see here, now, in number one function, the first function here, it's described as x equals, but it wouldn't be very difficult to describe it as a y equals, would it? We could say y equals x minus 1. However, number two function here, it'd be a little more complicated, I guess you might say, to describe this as a function of y. I mean, as a function of x. Because it's got y squared. So to get this to be a function of x, I'd have to have y equals something. And y would equal, well, we could say what it equals. It's the square root of 2x plus 6, but it's plus or minus. So no, this case, as this one strongly suggests, this is a case where I'd want to write, instead of y equals equations, I want x equals equations. So I'm going to change this one to be an x equals equation. How would I do that? Well, subtract the 6, divide by 2. So let's call it y squared over 2 minus 3 equals x. So we get both of our equations in terms of x equals equations, or as x equals equations. In other words, functions of y. All right, and we'll also see that this is the best way to go to because of the way the picture, the graph turns out. If we graph x equals y plus 1, what does it look like? Well, it's a straight line. The x-intercept's 1, and the y-intercept's negative 1. Right? This line here. What do you know about this? What shape is that? Parabola? Which way? Sideways parabola, yeah. This is a sideways parabola. X equals y squared over 2 minus 3. That's a sideways parabola. It's shifted minus 3, so it's shifted back 3. And it's a little bit wider, so something like this. These are a little more complicated, of course, to graph, but yeah, it's the x squared over 2 minus 3 graph turned sideways. So yeah, here's basically what we get. With me on that? Maybe a little wider. Sideways graph, back 3. So, okay. Set it out. So you see here, seeing the picture, I mean, we could do this with, as we were doing in dx's with integrating with respect to x. However, do you see I run into a slight problem, because if I do that, if I do it with respect to x, which are these up and down rectangles, I'm going between this curve and this curve, the same curve, basically. And then here I've had to split it up, because then at this point it takes over, and the bottom one is actually the line. The curve, in this case the parabola, the top curve and the bottom curve is the parabola, which they'd be square root graphs. But anyway, we don't want to do that. We want to integrate with respect to y, horizontal rectangles. Our typical approximating rectangles, we want them to go this way, because if we do that, we have a simple right and left functions, don't we? We've got the right function is the line, the left function is the parabola. Okay. So having said all that, yeah, we want to use the dy instead of dx. Okay? All right, so what does that entail? Well, it doesn't give me my points of intersection, so I've got to do that. Set the two parts equal. Find the points of intersection here. So that would be y plus 1 equals x squared, y squared over 2 minus 3. I'm going to multiply everything by 2. Get rid of that denominator 2. So it'll be 2y plus 2 equals y squared minus 6. Set this to 0, so I'd subtract 2y, so I have y squared minus 2y, and then subtract 2, I have minus 8. So the y values are going to be y minus 4 and y plus 2, positive 4, negative 2. Everybody with me on that? Okay? All right. So what's my integral that I use to find this area? Area that I want. What would it be? Negative 2 to 4. Do the right one minus the left one. So the line's on the right, so that would be the y plus 1. Minus the left one is the parabola one, which is y squared over 2 minus 3. Sound about right? With me on that? A little bit of simplifying, isn't it? We have negative 2 to 4, be y plus 1 minus y squared over 2 plus 3, wouldn't it? So it'd be, however you want to write that, minus y squared over 2 plus y plus 4, I believe. That's the way I see it. I combine all those together. Combine like terms. Huh? Okay. All right, so that would be a negative 1/2. I'll leave it in there, right in here. That would be a negative 1/2 times, what, 1/3 y cubed plus 1/2 y squared plus 4y from negative 2 to 4. So I have negative 1/6 times 4 cubed is 64. 1/2, 16 plus 16 minus negative 1/6, negative 8, 1/2 negative 2 squared, so it'll be 1/2 of 4, which is 2, minus 8. I believe we'd get it. Does that look okay? Mess anything up there? So that and a minus makes it plus. So it come out to be 1/6 times 64 plus that'd be 8 plus 24 be minus 8/6 minus 2 plus 8. 26. All those fractions we get a whole number. All right. Any question? One other quick little note here I have in my notes, and I think maybe it comes up in a problem. Let me mention it in the book. Any question on that? Got all that? Okay. If it says, and again it gets back to the what are they asking for, find the area bounded by y equals x squared. I don't know if I'll go all the way through this one, but just to make this point, y equals x plus 2 and x equals 4. Find the area bounded by y equals x squared, y equals x plus 2, and x equals 4. Different interpretations you can take on that, because here's what the picture looks like. Y equals x squared, looks like that. Y equals x plus 2, looks like this. And x equals 4, well, it turns out, I guess that point is 2, 4. Right there. And then x equals 4. So x equals 4 would be this line here, wouldn't it? Vertical line. So which part would you say they're asking you for? Well, what they're asking for, I believe, the region, the area bounded by all three. Which area is bounded by all three? It's this area right here. You know, if it were me, I'd be saying, well, here's also, I guess it doesn't say enclosed by, it says bounded by. So it's talking bounding by all three. So if that's the way it's worded, then they're looking for something that has all three of the functions, or how many ever functions it is, included as a boundary. That wouldn't be, yeah, that would be, okay, setting it up. Actually, since we don't have to worry about this, yeah, here's our top. Yeah. You want to do it with respect to x. So it would be the integral, the top is x squared minus the bottom is x plus 2. So this would be what you would do. And like I said, it's between 2 and 4. So but well, it gives me the endpoint because it's just a straight up and down line. Yeah. Yeah, if you did it with respect to y, that would be a whole nother issue because, yeah, you're talking between right and left here and then right and left here. So you've got to split it up. So you'd have to split it up if you did it with y. So you'd want to do it through that. Okay, but anyway, I just wanted to mention that. Bounded by, their meaning, bounded by all three. Kind of like the triangle we did earlier. Okay.